Okay, so the next thing to talk about is some applications of Ampere's law. We already saw one of them for a thin wire, but now we're going to look at the magnetic field created by a long current carrying wire that has some thickness to it, so we can find the magnetic field outside the wire, out here, as well as the magnetic field inside the wire here as well. Okay, and we're going to use Ampere's law to do that. And so just to rewrite what Ampere's law was again, we take the integral of the magnetic field, the line integral, over some path, and that should be equal to mu naught times the surface integral of j dot dA. And this problem, we'll actually be able to use this version of it. Okay, so outside, in this region out here, so this picture, I hope this picture is clear enough that I can draw on it for you guys. You have a wire that carries current coming out of the board. We imagine that we're just looking at a cross-section of the wire, but the wire basically continues, and we're just looking at some cross-section of it. And that wire carries a current I, right? And we want to calculate the magnetic field at different locations. The first thing I'm going to say is that the direction of the path is going to be the direction pointed by this ds thing right here. And that if we choose the region where the radius r, little r, is greater than big R, then I would say that the amount of current enclosed would just be equal to the current I in that region. And that means that by applying this, we get an answer that we've already kind of got. We just did it a second ago, which is that the magnetic field outside of the wire is just going to be mu naught I over 2 pi times r, where r represents the distance you are away from the wire. So that's the region r greater than r. We've already done that. The more interesting region, and this would actually be r greater than or equal to r, honestly. The other region that we want to look at is for r less than r. That is to say inside. Okay, that's the more interesting part here. So for little r less than big R, then we're looking for the magnitude of the magnetic field inside the wire. So this is inside wire. Now, what we need to do is we need to calculate the amount of current enclosed. And in this case, the enclosed current for path 2, so this is path 2 here, that little dashed path right there, is going to be found by doing this, this integral of j dot dA. How do we do that? Well, first of all, we can say that this is equal to current divided by the area enclosed by the loop. So this would be the area of the loop, okay? And in this case, our loop is that dashed line there, the blue dashed line. So if I say that the radius of this is little r, okay, to represent any value of r less than big R, then the area of that loop would just be the area of a circle of radius little r. So the area is just pi times little r squared. That's j. Okay? And it doesn't vary over the area. The area, just to be clear, is this thing here. And it produces an area vector that points in the same direction as the current. This would be what we would call dA. And j points in that same direction as the current as well. So j and dA are parallel to each other. And in addition, hold on a second, let me make sure I've... Current density is the current divided by... my bad. In this case, I represents the total current, right? So for the whole wire, my bad, this is wrong. Yeah. This is what the current density is. It's pi times big R squared, my bad. Because this is the area, not of the loop. It's my bad in this case. It's the area of the whole wire, or of the cross-sectional, it's the area of a cross-section of the wire. I'm so sorry about that. Of the whole wire. And the current is uniformly distributed. I should have taken some time to read this. Maybe we just do that now. A long straight wire of radius big R carries a steady current I that is uniformly distributed through the cross-section of the wire. So it's uniform current distribution here. So that means that this is true, that this is just a constant, basically. It's the value of the current divided by pi r squared. So if we pull that out of here, let me erase these two little, oops. Oh, it's not letting me. Here, we'll do this. So now what we get is that this equation, the j is going to come out of the equation. This is going to be I divided by pi r squared. And then the other portion of this is going to be the surface integral over dA. This is all just going to calculate what I enclosed is. And in this case, what this is going to be is the area of the smaller circle. That's going to be the area of the path. This right here is going to represent the area of the path itself. So the area of the loop is just going to be pi times little r squared. So that part is the area of the loop. And that's all equal to I enclosed. So we can simplify that by canceling pi's to get that I enclosed is equal to big I times little r squared divided by big R squared. It's effectively the fraction of the area, right? This is the fraction of the total area. Pi r squared over pi big R squared is the fraction of the total area enclosed by the loop. And that represents what I enclosed is in this case. The next thing we need to do then, does anyone have any questions so far? Okay. In this case, by the way, in case you're wondering what's going on with this dA thing, this integral here, dA in this case represents this. And you can see probably if you integrate this, right? If you integrate dA, it's pretty easy to see that you're going to get pi r squared, right? But I mention this because I know that the problem that I gave you guys in the lab manual and some of your homework problems, the j might not be constant. In this case, it's constant, but if it wasn't constant, like if j was equal to like kr squared or something, then you can see that you would actually need to do an integral. You know, you'd have to do kr squared and then 2 pi r dr, and you'd have to integrate this. It's an easy integral to do, though. It's basically just kr cubed, right? Okay, in this problem, though, this is what we have. I enclosed is this. And now we throw it back into our equation. So now we have basically, I'll write this over here. So now we're doing integral b dot ds. And this is the region where r is less than big R. We say that this is equal to mu naught times I enclosed, but we just calculated what I enclosed was. That's I times little r squared divided by big R squared. The left-hand side, we say the magnetic field in the region on the inside is going to be constant. We can pull it out. This ends up being the integral of ds, where our ds is the inner path now. And we have basically b times the path, which is now going to be 2 pi r. And that's going to be equal to mu naught I r squared over big R squared. And then we cancel the r's, and we end up getting b. This is going to be on the inside again. It's going to be equal to, what do we have left? Mu naught I. One of the r's cancels out. This r cancels out with one of these. So then we have just r. And that's divided by, 2 pi r squared. Looks right to me. This is for r less than big R. That's the magnetic field inside the wire. At the center of the field is 0. When like r equal to 0, you get b equal to 0. And if you let r equal to big R, you get the answer from the first part, which is this here. Like on the boundary, the two solutions match each other. That's the magnetic field inside of the wire as long as it has uniformly distributed current. Uniformly distributed current means that the current density is constant, like this right here, right? It's the current divided by pi times the total radius squared. If it's not constant, you need to evaluate this integral, and it's basically what you would have done in the lab annual homework. Do you guys have any questions? Does this all make sense? Ampere's law is pretty tricky. Or maybe it's just so confusing that you have no questions because you don't know what to ask. If that's true, go ahead and, just say I'm lost or something like that. You kind of, if you just vaguely get it, that's cool. We can keep going and give people a chance to ask. We're going to use Ampere's law two more times for a solenoid and a toroid here, so you'll see some more applications of it. But it's just like, do I really? Yep. That sounds about right, Desminster. Alright, so, this stuff is tricky. It's not made any easier by the fact that I made a mistake in the derivation right here. I really don't want to confuse you guys, it's just that this stuff is actually pretty tricky. A lot of tiny details you can't miss as I'm teaching it to you, but unfortunately I'm not perfect. I make mistakes. A lot. Okay, so that's the magnetic field inside the wire. That's the magnetic field outside the wire. Let's look at a couple more applications. So, the next application, this one's really important actually because solenoids are just found everywhere in electronic equipment, in your car, in all kinds of places. A solenoid, what is this? A solenoid is basically what happens if I take like some kind of a tube. Okay, let's say I have a tube, and maybe that tube is made of plastic, or it doesn't really matter what it's made of. The tube is basically just there to form a support. So if I've got a tube, okay, and again, this can be made of cardboard, it can be made of just plastic or something like that. Let's say it's made out of plastic. So a plastic tube, like maybe a PVC pipe or something like that, right? Just a tube, right? And then to make a solenoid, all you do is you take like copper wire and you just run it around it. And you run it around as many times as you possibly can, right? I'm trying to draw this wire kind of coming up around this way, and then it loops around the back, dot, 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 like that, and then it comes back up around here, and then it loops around the back, right? And then it comes back around here, right? So you just basically, you wrap as many wires as you possibly fit into this thing, depending on how much you want to. And the idea is that this is one continuous wire, right? It's one continuous wire. And then you need to have some kind of current flowing, all right? So let's say that in order to do that, right, you take, where's the back end? The back end of this would be coming out here. So now what you need to do is you need to have current flowing in it. And how do you get current flowing in it? Well, you can just put a battery in here, right? Positive into the battery, negative into the battery. That means that current is going to flow in this wire like this. And it'll flow up around like this, like this. Hopefully you guys get the idea. So a solenoid is quite literally a tube that is wrapped around with as many possible wires as you can get into it. And some of the features of the solenoid that we care about are the length of the solenoid, the number of turns, and what are called the number of turns per unit length. Those are the things we care about. Each one of these is what we call a turn of wire, okay? It's a turn. They call it a turn. So if it's wrapped 100 times around, there would be 100 turns of wire, okay? Does that make sense? So it's each loop of wire that you have wrapped around this thing right here. So we're going to use Ampere's law to find the magnetic field inside of this solenoid, okay? And in order to do that, what we want to do is we want to basically chop our solenoid in half, or at least look at a cross-section of the solenoid, okay? So I want you guys to imagine that we take this. I should have drawn it vertically, I guess, because the picture's vertical here. But imagine that we take our solenoid, right, and we want to draw what it looks like if we were to take a cross-section of it. This is what the cross-section is going to look like. And the reason why it's going to look like that is that we have these wires, right, where you have this current. In this case, you have current coming out over here, and then it goes back in on that side, right? And then you have current coming out over here, but then it goes back in on the other side, right? And I'll go over here a little bit. You have current coming out on this side, right, because it flows up this way, but then it goes back in on the other side, right? And hopefully you can get the picture of what's going on here and how this picture that I'm drawing on this side is comparable to the picture that we have over there on the left, right? Can you see the similarities? That basically, if I were to rotate this entire object like this, then each of these x's right here would represent a current I that's flowing. In this case, it flows out, and then on this side, it flows back in, right? So the dots and the x's right here, they represent the direction of the current, right? You guys, is it clear to you guys how this picture turns into that picture over there? I should have written, by the way, that this is just copper wire. It could be any wire. It could be silver wire. It could be, okay, so I guess it's clicking for some people. That's good. So this is our cross section. The reason why we do this is because it's going to be a little bit easier to apply Ampere's law. Okay, and that's what we want to do. We want to use Ampere's law for this. Again, Ampere's law, the goal of it is to calculate Ampere's law. The goal of it is to find the magnetic field. And to use Ampere's law, we need to use a loop. Okay? Now, there's a couple things we're going to say before we even start doing this. First of all, if I just had one loop of wire, right? And this was my loop of wire like this, okay? And I said the current flows that way, and this way, and this way, and this way. But it's oriented kind of horizontally, right? That's the direction of the current. Can you guys tell me, at the center of this wire, what would the direction of the magnetic field be? Would it be pointing up or would it be pointing down? The field, does it go up or down? It goes up, right? And then it also has these kind of loopy features like this, right? The magnetic field does. But we're not so concerned with that. Because when you start to stack a bunch of these guys together, these kind of loopy features of the magnetic field like this, well, they kind of start to disappear. Because if you get enough of these like loopy magnetic fields lined up together, then you're going to get a nice straight magnetic field pointing through the center, right? If every one of these loops produces a magnetic field at its center like this, but then you just start stacking loops together, right? I stack another loop exactly like this below it, and then I stack another like this exactly below it, right? You've got this series of rings. Then at the center, as long as the current's flowing in the same direction, you're going to get these nice straight magnetic field lines like this. Okay? I'm going to erase these things, but if one loop looks like that, multiple loops just keep adding together the magnetic field and it just gets straighter and straighter on the inside, right? So that's the reason why the magnetic field points the way that it does here. It points up because of the direction of the current, right? Because the direction of the current here, just to be clear, is it's coming out of the board here, but it's going back into the board there. So basically that represents basically a loop right here, right? Where the current goes out and then back in and then back around and then it just goes like that. That's the direction of your current for every one of these little loops. And that's going to produce these nice straight magnetic field lines that are drawn here, right? Hope that all makes sense to you guys. Okay, so Ampere's law, what does it say? It says we need to integrate along our loop the integral of b dot ds. And we know that that's equal to mu naught multiplied by the current that actually is enclosed by our loop. Okay, all the current that actually flows through our loop. Right? So this is our loop. I will draw it on here so it's clear. Our loop goes this way. Oh, it starts from here, right? So our loop goes this way, right? And then it goes this way, and then it goes that way, and then it goes that way. That's the direction of the loop that we're going to traverse right here, okay? It's broken up into 3 different segments, okay? 3 different segments here, right? And you can see the dimensions of the loop. It's W along the top, and it's L along the right side, okay? So let's evaluate b dot ds for every portion of this, okay? Keeping in mind that ds is simply a line element vector, right? That points in the same direction as the loop moves, okay? So if your path is like this, then your ds vector is like this, right? It's ds. So let's do this for all of our loops. Let's start for loop the segment that we call 1, okay? The integral b dot ds means take the value of b, okay? Let's split this up into 4 pieces, okay? So let's do this. I don't know how I want to do this. Along loop 1, what are you going to get? I'll write it above here. Along the segment of loop 1 that we call 1 right here, what are we going to get? The magnetic field in this regime right here, let's just go ahead and make the assumption that it should be roughly constant in this regime. That means that we can pull the b dot ds out of here. Notice that ds points in the same direction as b, which means it becomes just bs, or sorry, it becomes b times this right here. So I would say we're just going to get b times l. That's from part 1, okay? The part 1. For part 2, right? Now what happens is that along this line right here, b and ds are perpendicular to each other, right? If b and ds are perpendicular to each other, what are we going to get from b ds? We're going to get something like b times the length, which is w, and you're going to get 0, just like Tom Nook is saying here, because this is going to be multiplied by the sine of the angle between b and d, not the sine, sorry, my bad. It's dot product, right? It's a dot product. Dot products are cosine. Okay. Plus, we'll do number 3. So for number 3, we're going to say that you would get b times l. Your path is this direction. The magnetic field, there are some field lines out here, okay? There are going to be field lines that kind of go out this way and around back this way. I'll draw one more in here, but then I'm going to erase it. Some like that, right? You're going to get these magnetic field lines like that. It gets kind of messy to draw them. But what I'm going to say is that the field out here is very weak. In this regime. It's really small. So we're going to assume that the contribution from this part right here is going to be such that that magnetic field, and we might even call it B3 or something like this, the field in this regime out here, we'll call it B3, it's weak. So we're basically going to say that this is roughly 0. All right? This is something where I have a demo for this to prove that to you. We have a little magnet we can put up next to one of these solenoids, make current flow through it, and it's pretty easy to show that there's very little field on the outside of the solenoid. Okay, so there we go. We say that part's kind of weak, and then when we get to portion 4, as we're doing this, along that lower line right there, what's the angle going to be between B and DL? B and DS, sorry. It's going to be 90 again. So you cosine 90 again, so we're going to get another B times a W times a cosine of 90. And this portion is going to be 0 as well. So you get 0 for this, you get 0 for this. It's all equal to mu naught times I enclosed. Let's talk about what I enclosed is in this case. So let's count. If the current flowing in the wire through all the loops is just called I, right? So that's I, that's I, that's I, etc. Every one of those is I. Then in this case, what we have is we have 5 currents going into the page, right? There's 5 of them, right? So let's just say that we have basically mu naught times 5 times the current I. And that's multiplied by, well, that's it. This is basically the current enclosed. Hopefully that makes sense to you guys. We could have enclosed more loops, but that's how many we closed, right? All right, so now what we end up with is basically B times L is equal to mu naught multiplied by 5 multiplied by I, okay? Where L is, I've kind of blocked it off here, but I'll erase this to indicate what it is. L is the length. Oh no, it's doing that thing again. I think I fixed this if I just like do that. No, I haven't quite figured out what it's doing exactly here. Maybe I've clicked something that I'm not supposed to click. I mean, that does that. This, why won't it let me choose an eraser? Does that fix it? Oh, that's too bad. I don't know what to do. One thing I can do is this. Just delete that piece right there, I think. Okay. Yeah, so L is the length of this loop right here, right? It's the length of this side of the loop. So we get back on track. B times L is equal to mu naught I times 5. But then we divide the L over there. And we get this 5 divided by L. Okay, that ends up being our answer for what the magnetic field is. Except this 5 in here is very specific to the case that we've chosen. So let's generalize this. What would happen if we had made our loop twice as big, right? So if we had instead chosen a loop that went around, let's say 10 of these. How can I get 10? There's 3 here and there's 2 there. So if I made a loop like this, yeah, like this. If I did that loop, same direction, what would I have gotten for the orange one? I would have gotten mu naught times 10, but then what happens to the length now? How long is this side now? It's not L anymore, it's what? If I change the number of turns to 10, what happens to the length of wire? It's 2L, right? And the I is still here too, right? It's the same I, but it's 10I, right? Oops. So, ooh, it worked there. What? If anybody can figure out what I just did to make that work, let me know. Right, so it's... But you get the same answer, right? See, it's the same answer. It doesn't really matter. They're the same. Because if I increase the number of turns that I enclose, I also increase the length of wire that I've enclosed. So in general, what we can write right here is that a more general way to say this would be if I just change my mu naught to some number n divided by L, right? And then this quantity right here is basically going to be a constant. And it represents, what is this? It's number of turns per unit length. So it could be like, for example, an example of what this could be would be n over L could be something like, let's say, 200 turns, whoops, edge of the screen, 200 turns, this is really hard to write over here, per, I don't know, centimeter, right? It could be 200 turns per meter. If it's 200 turns per centimeter, that's a whole lot more turns in a tiny location, right? So we usually just simplify that. Different books use different things, but the symbol little n is going to represent the number of turns per unit length. And then we get a general expression for the magnetic field for a solenoid. And it is that the magnetic field of a solenoid is basically equal to, whoops, not B, is equal to mu naught, that's also mu naught right there, times little n, the number of turns per unit length, multiplied by I. And that is a really, really simple formula, actually, isn't it? It's like beautifully simple. As long as you know the number of turns per unit length and you know the current flowing in it, you've got the magnetic field produced inside the solenoid. The more turns per unit length that you get, the more finely packed you can get these wires up here. Like if you can put twice as many wires in the same length of tube by just continually wrapping wire after wire after wire after wire until there's just like, like a fishing line of wire around this thing or something like that, like several spools of wire, then you can get a huge magnetic field in just this way. Does that make sense? Not only is it this huge magnetic field, but in addition to that, it's also, it's straight. It's a straight magnetic field, right? It's a nice straight magnetic field. And that's powerful. I mean, the fact that you know it's uniform and straight means that a solenoid is effectively the equivalent of a capacitor, right? Remember, a capacitor was this device, and we can make it look really similar to this. So it's kind of different, but a capacitor was this device, right, where you have a positive plate, you've got a negative plate, right? And this produces an electric field that's really nice and uniform in between the plates, right? So the solenoid is really very similar to a capacitor in that sense. It's not exactly the same, but the field lines are this way and the field lines are that way or whatever, but it's very similar in the sense that it's this way you can produce this nice straight field that can be useful for doing whatever you want to do, whether it be what I did in my line of work, which is control charged particles, or whether it be producing something like this for a speaker or, any other type of electronic application. Solenoids are extremely useful. They also show up as the starter in your car, and we'll talk about how that works later on with Lenz's law. But solenoids kind of are ever present in physics. Do you guys have any questions? And this is for a long. So something I haven't really talked to you guys too much about, but this symbol right here, mu naught, it specifically refers to air or vacuum, okay? So I would say this is an air core solenoid because it would be the magnetic field produced inside the air. The thing is, though, if you want to make the magnetic field stronger, you can put a piece of iron in here. If you put a piece of iron in here, the magnetic field will be something like 100 to 1,000 times stronger because the value of mu naught depends on the substance. Mu naught is a fixed value, but mu for iron, I don't remember the number for this, is something like on the order of maybe 100 times or maybe even 1,000 times. Off the top of my head, I just don't know what it is for mu naught. And so that you can produce an even bigger magnetic field by putting an iron core inside of here. Not to mention, you could also use this as a way to magnetize, and this is how you magnetize a piece of iron, right? You put a piece of iron inside of this, and all of a sudden the iron is going to have all of these magnetic kind of domains and spins start to point kind of in the same direction, and you can make a bar magnet out of this. You can make a permanent magnet by placing it inside of this for a long enough period of time. You can make it even stronger if you heat the magnet up and crank the current up really high, and then cool it down. Anyway, that's the magnetic field due to a solenoid. Anyone have any questions? Did that derivation make any sense? I hope that the solution, or like what you use, it's a pretty simple equation. You just take this constant mu naught, number of turns per unit length, times the current. And we've got this little quick quiz for you guys to think about here. Any questions at all before we do this? Notice the radius doesn't show up, right? Which means that the value of the magnetic field on the inside is roughly constant. So this is the quick quiz, the little question here to kind of think about. Consider a solenoid that is very long compared with its radius. Okay? It's very long compared with its radius. What does that mean? Well, that means that it's like skinny. Right? It's kind of skinny. It's long. And it's a solenoid, right? So you've got all these wires that are all wrapped around this, right? What is the most effective way to increase the magnetic fields in the interior of the solenoid? This is basically on the inside. Okay? There's, a few options here. You can double its length and keep the number of turns per unit length constant. You can reduce its radius by half, keeping the number of turns per unit length constant. C, you can overwrap the entire solenoid with an additional layer of current carrying wire. All right, so do you double the length, keeping the number of turns per unit length the same? Do you reduce its radius, or do you overwrap the entire solenoid with an additional layer of current carrying wire? Okay, which one of those will be the most effective way to increase the magnetic field in the interior? Can we picture a line? Kind of? You mean like just a line that's wrapped just in wires like this? Is that what you mean, Tom Nook? I mean, it's skinny, but not so skinny that there's not some size to it, right? Because you need to be able to have a loop to actually wrap around it. But yeah, it's a really skinny tube with these wires very tightly packed. If you guys want to answer, take a time to think about it. I'll give you a minute or so. Read the question again. Look at the formula right here. N is this thing is what N is, right? In case you don't. Oh God, no. There's some lag with the program there. This is N, number of turns per unit length. So read the question, type your answer in chat whenever you're confident of it. How long have I been on mute? Oh my god. I'm so sorry. How long was I on mute there? I was like asking you guys questions. I was like, no one's responding. Oh my god. Let's briefly go back through what I was saying. I don't know how long. Was it like a really long time? Okay. After I told you guys to try it. Okay, well, clearly you guys have had a lot of time to think about this. So that's good. So, all right, this is what I was trying to say. I said, what happens in part A? It says double its length, keeping the number of turns per unit length constant. And then you guys kind of figured it out as I was saying things, so it almost sounded like you were listening. But yeah, basically what happens in part A is that n stays constant because you've doubled the length, but you've also doubled the turns. That's like the 10 and the 5 and the 2 and the... Yeah? You guys okay on A then? Okay, cool. Part B, if you reduce its radius by keeping the number of turns per unit length constant, the thing is that no radius shows up in this equation, right? We're already kind of working with the assumption that it's very long compared to its radius, right? And that by reducing the radius, there's not really going to be any change. So C, overwrap the entire solenoid with an additional layer of current carrying wire. So I was saying if you start with 10 turns per meter and you wrap another 10 turns per meter on top of it, you've got 20 turns per meter now, right? And that's going to have the effect of making the magnetic field double, basically. Sorry, I was silent for so long. I didn't mean to do that. But do those things make sense? So the right answer is C, which is what everybody guessed, basically, to begin with anyway, which is good. Any questions about that? Well, the reality is that if it's like fat, so if it's like this, right? If this is the length, but that's the radius, then this equation's not very good anymore because this is going to start acting like a regular wire, and it's going to have these like loopy magnetic field lines, right? This would be like, so you'd have to have some wire in here too, right? So if you have wire that carries current like this, yeah, that's pretty much the best answer, what you just said. These loopy things right here. And then the field is like stronger at the center than it is on the edges, basically, in this case. But this equation pretty much refers to long compared to the radius. So that reducing the radius really only changes like the location of the magnetic field. There's a lot of vast oversimplifications happening here, but the goal here is to just get a rough idea of the magnetic field that's produced by a solenoid. That's like a quick kind of calculation you can do. And that is a pretty simple equation, I hope. All right. Do you guys have any questions? Does it make sense why C is the right answer? You can also increase the magnetic field, right, by increasing the current. One other thing I said probably while I was muted. I know when I muted myself. I muted myself when I looked this up. So the magnetic fields inside of iron would be about 200,000 times greater. And what I mean by iron, I mean you put the iron actually inside of the core, if that makes sense. Yeah. And it increases this quantity, mu changes to the magnetic, we call it magnetic permeability of iron. Okay. Hopefully that was helpful. Hopefully that made sense to you guys. We have a couple more of these to do, but now is a good break time because the next one will take probably about 10 minutes at least too. So let's take a break till 4 o'clock. That'll give us another hour or so. And before I do go on break, do you guys have any questions? Stop the recording.